This video is all about chemical reactions because we want to be able to write and balance chemical equations. So chemists use chemical equations to describe chemical reactions. These are like our sentences. These sentences describe what is happening in a chemical reaction. So again, think of an equation as a sentence that describes a chemical reaction. A chemical equation uses chemical symbols. So, think of those as our element symbols to indicate what changes occur during a chemical reaction. So, we'll have changes from elements to compounds. We'll, break up some compounds, form new compounds. That's the kind of thing we're doing in chemical reactions. So we'll have reactants and products. Reactants are written to the left of an arrow, and products are written to the right side of an arrow. So really, we'll have, kind of this general format where we have reactants go to products. And when I say go to, I mean with an arrow, go to products. That's our general format in a chemical reaction. We're going to have state symbols. G is for gas. A lowercase l in parentheses is for liquid. S is for solid. AQ is for aqueous, as in dissolved in water. Think agua, right? We're meaning water. And we see that used a lot, like aquifer and is water storage underground, for example, an aquatic center, and agua also means water. So AQ, or dissolved in water. Then we have some symbols, some energy symbols. This little triangle or delta is for heat energy. So let's say that there is heat energy going into the equation. We'll use that delta. And then we have this H nu means that we have, we're giving the reaction energy in the form of light. So E equals H nu is an equation that uses H, Planck's constant, times, it looks like a little V, but it's really a Latin V, or the Greek letter is actually nu. The Latin V is for velocity, and it's already used for velocity. So this nu here is about the frequency of light. So it's really Planck's constant times the frequency of light is equal to energy. And I mean, the point here is just that we've got energy in the form of light, that we're going to be giving this reaction energy in the form of light if we see H nu being used. Okay, subscripts are going to be the small numbers that tell us the amount of atoms in each molecule or formula unit. So think H2O. Well, there's two O's and then there's an implied, there's two H's, H2, two H's, and an implied one oxygen atom. Now, it doesn't say one oxygen here, but that's implied. So the subscript 2 really tells us that there's two hydrogens for every one oxygen. Coefficients are the number in front of a substance. They tell us the number of those compounds or molecules that are involved in a reaction. So let's just say that there was a 2 in front of water. That would be a coefficient. So this would be an example of, oopsie, I forgot that E, and I'm about to forget the E in coefficients. That would be an example of a coefficient. And the little 2, that would be an example of a subscript. So we've got subscripts and we've got coefficients to think about. So 2H2O means I have two of the water molecules. It really means I have one water molecule and then I have another water molecule, or 2H2O. So both subscripts and coefficients play an important role when we're writing out chemical reactions. Okay, next we're going to go over the law of conservation of mass, or law of conservation of matter. Sometimes it's called the law of conservation of mass matter. It really says that matter, and therefore atoms, are neither created nor destroyed in chemical reactions. So, you know, all matter is has mass, so all atoms have mass. In other words, all matter is made up of atoms. They have mass. That mass, that matter, can't be created, it can't be destroyed in a chemical reaction. There has to be careful accounting for all of the atoms. Why? Because they have mass, because they matter. They are matter. So in a chemical reaction, all the atoms present at the beginning are still present at the end of the reaction. That's really important. So if we think about the combustion or the burning of methane, you know, most of us burn methane or natural gas in our home to heat our home, to heat our hot water. We might use it at our stove top. We might use it in our fireplace if it goes on at the flip of a switch. Most of us burn methane in our clothes dryers at home, so we use this a lot. And so this is a great chemical reaction to kind of look at the law of conservation of mass. So if we look at it, methane CH4, G for gas, reacts with O2, G for gas, to form CO2 gas plus H2O gas. So we can do some careful accounting for the number of atoms on each side of the reaction. So if we look at the reactants, CH4 contributes 1 carbon atom. It also has 4 hydrogen atoms. We do an oxygen count. There are 2 oxygen atoms on the reactant side. On the product side, there's 1 carbon. There are 2 hydrogen atoms. And then CO2 has 2 oxygens plus 1 for the water is 3 total oxygen atoms. So this chemical equation is incorrect. Number of atoms present at the beginning is not the same as the number present at the end. To show that the reaction obeys the law of conservation of mass, the equation needs to be balanced. That's what we've got to do. We've got to balance this. Our equation needs to be balanced. So let's try to correct this. What we can do is, again, we can account for these and go, okay, well, what can we do to correct this? Here we had 4 hydrogens on the reactant side and only 2 on the product side. We can double the hydrogen count by putting a coefficient of 2 in front of the water molecules. If we have 2 water molecules, we won't just have 2 hydrogens anymore. Now we'll have 4 hydrogens on the product side to be balanced with the 4 on the reactant side. Great. What about carbons? They were always balanced 1 and 1. So ideally we wouldn't change that. What's going on with oxygens now? Well, now we have 2 oxygens from CO2 plus 2 from the 2 water. So we have 2 and 2 more is 4 oxygen atoms. To have 4 oxygen atoms on the reactant side, we'll have to double O2 or put a coefficient of 2 in front of it so that we have 4 oxygen atoms. So now this chemical equation is correct. To obtain the number of atoms of an element, multiply their subscript by their coefficient. In other words, if you want to figure out, okay, what's happening when I put a 2 in front of water, I really take 2 times the coefficient 2 for hydrogen is 4 hydrogen atoms. So I'm really multiplying. I'm assuming there's a coefficient of 1 for oxygen. 2 times 1 oxygen atom is 2 oxygens here plus 2 here is 4. So I'm really multiplying. 2 times 2 for O2 gives us our 4 oxygen atoms. So we multiply a coefficient by a subscript and we find out how many atoms of an element. Okay, so what are our general rules for how to write balanced chemical equations? We write the reactant and product formulas, all of the formulas out. We keep track of the number of each element on both sides of the reaction with a table, just like you saw me filling out. Then we balance one element at a time by inserting coefficients in front of the various elements or molecules to try to balance things. First, balance elements that occur on each side only once. Balance any lone elements in their elemental state last, like O2. So by lone elements, we mean those in their elemental state. They're easiest to do last. Elements that occur multiple times on each side, you really want to save those for later. You don't want to balance those first because they can just be, I like to call them troublesome trucks. They can be troublesome trucks. Oh, I actually had written there in their elemental state. So I already had it for myself. Okay, let's try this first example. It says hydrogen peroxide decomposes into water and oxygen. Sometimes this demonstration is called elephant's toothpaste. When you add this catalyst to hydrogen peroxide and you use some soap and it really bubbles and foams over, and you can search for some videos of that if you want, or maybe I'll post one, but they're kind of fun. So it says write the reactant and product formulas and count the number of atoms on each side. So let's try this one. So H2O2L for liquid has 2 hydrogens on the left and 2 oxygens on the reactant side on the left. On the product side, there's 2 hydrogen atoms, but with oxygen, there's 1 here plus 2 more is actually 3. So that doesn't work. To pick, let's pick an element to balance. So since hydrogen is already balanced, we pretty much have to pick oxygen. We don't really have another choice. Okay, so let's figure out how to balance it. One trick that I always use is, if an element is even on one side of the reaction, you pretty much have to make sure that it's going to be even on the other side. So since oxygen here is even with a 2, that's fine, but having there be 1 oxygen here and having it be odd, that's not going to work. You're never going to be able to take an even number and an odd number and get an even number. We actually are going to have to get everything up to being even, really by doubling this water. So when we put a 2 here, we have 2 O's now, plus 2 more O's is a total of 4 oxygens. And now we have 2 times 2 is 4 hydrogen atoms as well on the product side. Now we can see how, by getting to 4 and 4, we can just double our H2O2, our hydrogen peroxide. Put a 2 in front of hydrogen peroxide, and now we've doubled to 4 of each. So that's enough to balance it. So again, this is a fun little one called elephant's toothpaste if you want to look for it. I like to do this one. It's a cool one. Okay, and think about that idea of a catalyst because it's something that speeds it up and makes that reaction go a lot faster. So that's kind of fun, and an idea that we'll come back to as well. Okay, so here's another one. When magnesium metal burns in air, it produces a white powdery compound, magnesium oxide. It says write the reactant and product formulas and count the number of atoms on each side. So we've got magnesium solid plus oxygen gas, O2 gas, makes MgO solid. Okay, so let's do our element count. We've got 1 magnesium on the reactant side and 1 on the product side. We've got 2 oxygens on the reactant side, but only 1 on the product side. So pick an element to balance. Since magnesium is balanced, pick oxygen. And let's figure out some coefficients. Again, we've got even, oxygen O2, but here's 1 oxygen. We're going to have to make that even. We're going to have to put a 2 there to get us up to the evens. So on the product side, then we have 2 Mg and 2 O. And now on the reactant, we have 1 Mg and 2 O. So in order to balance oxygen, we actually then made magnesium unbalanced. So when we recount, magnesium is actually not balanced now, but that's okay. We're just going to repeat attacking the unbalanced element. So when we repeat to attack the unbalanced element, we already put a 2 in front of MgO. So we have 2 magnesium, 2 oxygen. Oxygen's good, but we have to double or put a 2 in front of magnesium because we have to attack that last unbalanced magnesium and double it to make sure it's balanced. Okay, we have one more key type of example to go through for balancing, and that's really when we encounter polyatomic ions. So, example 3, sodium phosphate reacts with magnesium chloride to produce the white precipitate, magnesium phosphate. Okay, so what do we do here? Well, one key way that we can tackle polyatomic ions is if we see a polyatomic ion like PO4, first recognizing it, calling it out, and then let's keep it together for the sake of balancing. Could we balance the phosphorus and oxygen separately? We could. It ends up being a lot more work though. A lot of multiplying in big numbers of oxygens, and it would be kind of frustrating. So it's really better to keep that polyatomic ion intact, counting it as a whole group. That's really how I would usually tackle this. So we've got Na3PO4. That'll be 3 sodiums and 1 of the whole PO4 group. And that's aqueous plus MgCl2 aqueous. Okay, that's 1 magnesium and 2 chlorines. Reacts to form NaCl aqueous. Okay, so that's 1 Na and 1 Cl plus Mg3PO4 2, and that's a solid. Okay, so we've got 3 magnesiums, and we've got 2 of the PO4 polyatomic ions. Well, then you just sort of tackle this one at a time, picking something that's not balanced. Okay, sodium's not balanced. Let's put a 3 in front of NaCl on the product side to get it balanced. So that changes Na to 3 and Cl to 3. Then we might go to phosphate and go, okay, how do we get PO4 balanced? Well, let's go ahead and put a 2 in front of Na3PO4. Remember these multiply though, so 2 times 3 Na is actually 6 Na. Oh no, I thought I just got it balanced. Maybe I didn't. Now this means that I have 2 of the phosphate groups, so I'll balance that. So much for phosphate being, and that one's balanced, so we can kind of be done with it. Now we've got 1 magnesium and we've got 3 magnesiums. Well, if I put a 3 in front of MgCl2 on the reactant side, I'll have 3 magnesiums, and 3 times 2 is 6 chlorine atoms. Remember that these multiply, so 3 times 2 means there'll be 6 of the chlorine atoms. So when I'm looking, phosphate is balanced and magnesium is balanced, but Na and Cl are not. I need 6 of each of those. Unfortunately, I put a 3 here, so I've got to get rid of that 3. I've got to actually change that 3 to a 6 so that there are 6 sodium atoms and 6 chlorine atoms. So don't be afraid to, put a coefficient on the line, cross it out, get rid of it if you find out later that it's incorrect. Now, it's important to talk about what to do with a blank, coefficient line when we're done. What you can do here is you can leave a blank, or you can put a 1 there. If you kind of want to remember that you finished this problem or show that you've finished the problem, you can put a 1 there. So basically, you can put a 1, or you can leave one of these blank. But the only thing you can't put there is, never a 0. The reason that we don't put a 0 there is because we wouldn't want to indicate that we have no magnesium or no phosphate on the product side, because then it would never be balanced. So you can do a 1 or a blank, but never a 0 on one of those coefficient lines. Okay. Next up, we're just going to practice some more balancing. This is a great time to press pause and try these practice problems on your own. So if you press pause and you tried some, now I can go over them with you. Why not? Okay, let's make element lists down the center. Let's go aluminum and oxygen, and I sometimes put little lines here on the reactant and the product side. I always do them right where the arrow is. I don't know, that just helps me. So I've got 1 aluminum on the reactant side and 2 oxygens on the reactant side. I've got 2 aluminums on the product side and 3 oxygen. So I want to pick something that's not balanced. I might do aluminum right away, but I'm getting suspicious after that last one that maybe I should wait on it. Should I try oxygen? This is a common problem. To have one oxygen be 2 and one be 3, we need to get up to a common multiple. And the common multiple of 2 and 3 is 6. So we need to get both sides to 6. So we'd say, okay, I'm going to put a 3 in front of O2 because 3 times 2 will give me 6 oxygens. I'm going to put a 2 in front of Al2O3 because 2 times 3 will give me 6 oxygens. And aluminum is going to change to 4. How did I know? Well, I knew these problems ahead of time, right? 4 in front of aluminum on the reactant side will change it. So we've got a 4, a 3, and a 2 to balance that one. Okay, next up, H2S gas. So we've got hydrogen here, we've got sulfur, and then plus SO2, so more sulfur and oxygen. So SO2 gas reacts to form sulfur solid and H2O liquid. Okay, so 2 hydrogens on the reactant side, 1 sulfur and 1 more sulfur is 2 sulfurs. 2 oxygens on the reactant side. On the product side, we've got 2 hydrogen atoms, we've got 1 sulfur atom, and we've got 1 oxygen atom. So it actually looks at first like hydrogens are balanced and sulfur and oxygen is not. Okay, well, we need to double things, get things even here. If I put a 2 in front of water to get 2 oxygens, I'll change the hydrogen count to 4. Well, what next? Should I double my hydrogen count on the reactant side? I would have to put a 2 in front of H2S to get to 4 hydrogen atoms. Now I have 2 sulfur plus 1 more sulfur is actually 3 sulfur atoms. And the last thing I need is just a 3 in front of sulfur to get 3 sulfur atoms. Now I can leave this blank or I can put a 1. Just don't put a 0 in front of SO2. And that one's balanced. Okay, now here's one with polyatomic ions. Do you see any polyatomic ions? In the parentheses are a real clue. They are for sure inside the parentheses. SO4, the sulfate, and OH, the hydroxide, which is in parentheses here. Those are polyatomic ions. So we can list those and keep them together. So we've got iron, then we've got SO4. Keep it all together and count how many are on the reactant and product side of that polyatomic ion. Na for sodium and OH for hydroxide. Okay, so let's do some counts. 2 iron, 3 of the sulfate ions on the reactant side, 1 Na and 1 OH. On the product side, 1 iron, 1 sulfate, 2 sodium, and 3 hydroxide. Just start balancing things that aren't balanced. 2 iron on the reactant to get 2 on the product side. Let's do 2 iron, 3 hydroxide. So let's do 2 Fe's. And then OH is 2 times 3 here. Sorry, that was supposed to be towards 3. 2 times 3 would be 6 of the OHs now. Let's see, we need 3 sulfate. Let's go 3 in front of Na2SO4 so that we get 3 of the sulfate groups. We'll have 3 sulfate groups then, but we've also changed Na because now it's 3 times 2 or 6 of the NAs. So remember that we're multiplying. Now we need 6 NAs and 6 OHs. Oh, that's easy enough. Put a 6 in front of sodium hydroxide. 6 NAs and 6 OHs. And again, we can leave this line blank or put a 1. Just don't put a 0 and you're all balanced. Okay, we've got another example, combustion of ethyl alcohol in flambe, a brandied flaming dessert. So they can use ethanol in order to make some of these desserts. They kind of light the alcohol on fire that they put on. It would be like the alcohol in brandy would be flammable and they can light it and kind of give the dessert a crispy finish. That's kind of fun. Okay, let's write all the elements we've got here. Carbon, hydrogen, and oxygen. So On the reactant side, we've got 2 carbon atoms, we've got 6 hydrogen, and we have 1 plus 2 more, 3 oxygen atoms. And on the product side, we've got 1 carbon, we've got 2 hydrogen atoms, and we've got 2 plus 1 is 3 oxygen atoms. Okay, so let's try balancing this. Well, the carbons aren't balanced. Let's double the CO2. We'll have 2 carbons then. Then we'll have 2 times 2 is 4 oxygens plus 1 more is 5. Ooh, that's kind of looking like a mess. But remember, we were going to do elements in their elemental state last. So for sure, just leave the O2 because that's kind of a rule of thumb. Okay, so hydrogen, well, we need 3 times as many here on the product side. We need 3 times 2 will give us 6 hydrogen atoms. Now what's our oxygen count? 2 times 2 is 4 plus 3 times 1. We actually have 7 over there. If you want to see that math for oxygen, 2 times 2 plus we've got 3 times an implied 1. So plus 3 times 1, or the oxygen count is actually 4 plus 3 is 7 right here. Okay, well, how do we get 7 over here? Well, we subtract out this one. So we really go, okay, 7 minus 1 is 6 divided by 2. We should put a 3 here. We'll have 1 plus 3 times 2. We'll have 6 plus 1 is now 7 oxygens on the product side. So we have 7 on the product side as well. So again, if we're trying to figure that out, how do we get 7 over here? Well, we do 7 minus this 1 that's already here is 6. And we need that 6 to be divided by 2 because every molecule is going to have 2 oxygens. So there'll be 3 up those O2 molecules then. And we can leave this blank or we can put a 1. You can tell I kind of have a preference for putting 1 on the line. It just kind of shows the world that I finished that problem and I'm sure that I'm done with it. Okay. Let's try this last problem. In this one, we're going to write out the chemical equation ourselves. So it says potassium hydroxide. We find potassium on our table. It's group 1A, so it's K plus 1. Hydroxide is one of our polyatomic ions. We know it's OH minus 1. And then it reacts with, so that's going to be a plus. With is going to be plus, aluminum chloride. So we find aluminum, it's in 3A, so it's Al3 plus. Chloride is a halogen, so it's minus 1. So it's going to take 3 of those chlorides to give. That's where we have our arrow. And then we'll have potassium chloride, so K is a plus and Cl is just a minus. And aluminum hydroxide. Okay, well, we already said Al's in the 3 plus column. OH is minus 1, so it will take 3 of those in this particular problem. Okay, so we can see some 3-to-1 ratios. We're going to need some balancing here. Okay, so let's just rewrite this. K plus OH minus is KOH. Reacts with is a plus. And I'm going to leave myself lines for balancing. Reacts with aluminum chloride. Well, that's AlCl3. There were 3 of those chlorines. To give, there's our arrow, potassium chloride. So I'm going to put a line, put my KCl, plus, and then put a line, and put my aluminum, and then I need parentheses around my OH because there's going to be 3 of them. Okay, now that I've got this rewritten, we can balance it. Let's look for our polyatomic ions, though, and keep them together. Balance OH as a group. Because it's a polyatomic ion, it's just slightly easier to do that than splitting out O and H separately. So we've got K, we've got OH groups, we've got Al, aluminum, and we've got Cl, chlorine. Okay, on the reactant side, 1 potassium, 1 hydroxide, 1 aluminum, and 3 chlorine. On the product side, 1 potassium, 1 chlorine, 1 aluminum, and 3 hydroxide. Well, let's just start tripling things. First, let's triple the hydroxide on the reactant side, which triples the potassium and the hydroxide both. And then on the product side, let's triple chlorine by putting a 3 in front of KCl. So that makes 3 potassium and 3 chlorine, and everything's balanced then. I like to put ones there, so I like 3, 1, 3, 1. And that gets it all balanced. So now we've learned all of the kind of tips and tricks for balancing chemical reactions after we write them out to follow the law of conservation of mass matter.